Okay, well, in the absence of Chris for the moment, then Tony has to depart fairly rapidly, so we'll move to having the statement of accounts first. So, Tony, if you'd like to launch into your statement of accounts, please.
Okay, I will. I'll just get my sharing sorted out. So you should now all be able to see the statement of accounts, which I've received back from the auditor today. I have some notes to these accounts, which I'll go through separately, but these are available to be discussed. So the main thing to talk about, the effect on income and expenditure during the year was, as we all know, the impact of COVID. So consequently, we held no face-to-face meetings during the financial year that's just ended. For those who aren't aware, our financial year runs 20th of July to 20th of July each year. It's based broadly aligned with the academic calendar is the reason for that, I believe. So because we didn't we didn't receive all the sponsorship that we'd hoped for, and that was reduced, and also was our main source of income is always the Institute of Materials, and that was, as you can see on these accounts, I'll make them slightly bigger. On last year's figures, that was lower than what we would normally receive, and this year's was low still. Bank interest fallen off the cliff. That's rounded up. It's £2 something actually we got. So the financial year that has just ended, we had an income of £4,098. As you can see, there was no other social events or anything of that ilk. The subscriptions, as you see there, look as though they're significantly reduced, but I believe there's two reasons for that. One is that we're seeing the impact of people of increased life membership coming through. So more and more people have paid up for life membership over the last few years, and so consequently there's no further income expected from those. And also we normally would recruit people into the institution at face-to-face events, and we've not had the opportunity to do that. So the number of new members has been down as well. Expenditure. Our biggest expenditure normally is honoraria, but after that it would be meeting expenses. And as you can see, in that financial year there was 0 meeting expenses, so that made a big difference to our cash income and outcome situation. We gave one prize out in the financial year we're talking about, which was the Young Persons Lecture Competition winner. That was £100 to James Balmer. We did not award the annual award within that year. The only other significant piece of survey expenditure is this 169, which is in the main the costs associated with we still maintain a web domain, which we pay approximately £30 a year for, but the biggest expenditure there is for this medium that we're on now, which is the WebEx, which we pay £15 a month for that, which is, has been worthwhile. So if you look at the income over expenditure for the year just finished, it's a positive figure of 1,179. And you put that against the figure for the previous year, which was partially affected by COVID, where we ran at £621 down. The assets we hold have also increased. So sorry, I did not cover the detail of the Institute of Materials grant. They significantly reduced the grant that they gave us in the last year to take account of the fact that all the societies were holding virtual meetings. The grant calculation for the coming year is being put together in a similar vein. But what they have done is they've made the entire process online. So I cannot, at this moment in time, say what expected grant we will have from the Institute of Materials, because I don't get the opportunity to see that until I've completed the online application. It's something that I'm in the middle of. The deadline is the 17th of October. And even though we've had virtual meetings, there's still questions in there about attendance. So I will need to speak to them and ask how they really, what kind of attendance records are required for that. I suspect they've not updated the form fully yet. The balance sheet shows that the assets, this is where we were at the end of the year, they'd increased by 1,000, just over £1,000. You can see it's gone from 40,416 to a value of 41,525. That includes the debtors. That's not cash in bank. If we look at cash in bank, the difference is that last year we had £40,066, and this year we've got 41,175. So that's the full book of accounts. The only thing I do need to add, and I'll bring my my notes across, which are available. Normally we would print them out, put them on the chairs. Is this point at the end? Some of you may be aware of this, but after the year end, we had problem with our bank accounts, which resulted in us temporarily being unable to process funds. I mean, we couldn't receive funds, but also we couldn't pay any. But fortunately, we didn't owe anybody any money. This came as a result of the bank wanting to change the type of account that we have based on the fallout from significant changes in banking regulations over the last few years, so that they make sure that people are properly regulated. So I'm in the middle of that process now. So as we stand presently, the bank account is operational. We can receive funds. So if people have subscriptions that are due, those payments should be going through now. The likelihood is that we will have to change the type of account we have. So at some point in the near future, we most likely have a new sort code and bank account number, which we will communicate as soon as that's clear. So that's really all I wanted to say. Has anybody got any questions relating to those accounts as they stand? They are currently, they have been audited, but it says in my notes there they are unaudited. That is because at the moment I'm not in receipt of the signed copy. But that is just something that the auditor will send me when she's been able to scan the copy that she signed. So I don't expect those figures to change.
Any questions for Tony? If your microphone is muted, I believe if you press the space bar, that will unmute it temporarily if anybody is shouting at their computer and wondering why we're not taking any notice. No? Okay then. Right, thank you for that then, Tony.
Apologies, as I've explained, I do have to leave, so take my leave and goodbye.
Okay, thanks very much, Tony. Right, well, in the absence of Chris Beck, our outgoing president, I guess it falls to me to welcome everybody to the AGM. We have an apology from Graham Hillier. He's having computer problems, unfortunately, and can't get logged on. So I'm afraid we'll have to manage without Graham. Do you have any other apologies, James? You're on mute.
No, I haven't received any other apologies.
Right, okay. Well, we've had the statement of accounts. The next item on the agenda is the election of council membership. I did circulate in a newsletter. Joanne, could you share this page with the list of the council, please?
I will have a go at that. Just a minute. I think I closed it down. Just a sec. Apologise. There it is.
Well, whilst you're trying to get that to come up,
Sorry.
Um,
Yeah.
basically 3 members of the council stand down each year, and they're the ones who have been on the council for the longest time since their last re-election. And this year it's myself, Vince Ludlow and Don Spenceley who are standing for re-election. I'm not sure what's the best way to do this. Oh, there we are.
Can you see
It's
that okay?
page 2. Yeah, scroll down, Joanne. It's page 2 of that document. Just so people can see who is actually on the council at the moment. Yeah, that's it. So at the bottom there, you can see it's myself, Vince and Don for re-election. I'm not sure quite what's the best way to do this on a video call. I think probably the best thing to say is, does anybody have any objections to myself, Vince and Don being re-elected? Speak now or forever hold your peace and all that.
Okay, so would you like me to propose that all 3 of you are re-elected?
Yes, I think that would probably be helpful, Joanne.
And if somebody else could second that?
I'll second it, Joanne.
Thank you.
So in the absence of any loud protestations, I declare we've all been re-elected. Oh, I should also
Excellent.
add that Paul Shelton has resigned from the council since last year's AGM. He's retired from paid work and has decided to resign from the council as well, although I hope we'll still see him at meetings. Right, okay. Normally now we would have a president's report, outgoing president's report, but since we don't have the outgoing president with us, I think we'll have to skip to that. We do have a nice photograph of a handover of the medals, which I will put in the next newsletter so that you all get a chance to see it. So I think without further ado, it's over to you, Joanne.
Right, well, I haven't got anything to comment on, but I have got some comments. I'd like to thank Chris for his year of presidency and his excellent chairing of meetings and enthusiasm for the role. He also, helped identify some really interesting talks for the lecture committee. I'm sure you agree, Sue. And he's agreed to continue to help identify some good speakers and potential visits for the coming year. He will continue to support us with that. And what's really good is that because of his contacts and hopefully because of other people's contacts on the committee, we're able to get some really good speakers about some exciting developments on Teesside. And so that's really my comment, is about we've put together a programme for this year, which hopefully will showcase some really excellent work that's going on Teesside and some exciting programmes for engineers to work on, including hydrogen, plastics recycling, materials for batteries, things like that, which are, hopefully will contribute to the ongoing growth of Teesside industry. So those are just a few comments that I've just put together, winging it, but I'll hopefully we'll get a report from Chris that we can circulate, and I'll put some written comments on that. Does that seem reasonable, Sue?
Yes, that's excellent. Thank you, Joanne.
Okay. So I'm going to stop sharing now. Is there any more AGM business, Sue?
No, not really. I think the next thing on the agenda is your presentation.
Okay, so it's more of me. I'll appreciate some comments of whether I'm sharing the right screen. Just bear with me a second while I start from the beginning. I'm guessing that you can see the wrong screen.
That's the preview screen, yeah.
Yeah, okay, so I've got...
That's the right one.
Brilliant. The default always seems to be the wrong one. Okay, well, thank you very much for inviting me to speak today. It's a great honour to be invited, to be president and elected as president, but also to give a talk today. And this is my first speech as CIE president. Many of my predecessors have had significant positions in Teesside's steel industry. I didn't have the honour of working for the steel industry. I worked in the chemical industry, so I thought it might be interesting for people to talk about to hear about some of the wide range of materials that I've worked on when I worked in the chemical industry. So just to give a brief introduction, by the way, I'm probably going to talk for about 35-40 minutes. In normal case, I'd ask for interruptions, but questions as we go along. But I don't think it's this format really lends itself to that. So I'm happy to answer some questions at the end. So my career. I actually intended to be a chemist initially. When I was at school, I loved chemistry, and I went to university to study chemistry. But my attention was grabbed by the material science course when I probably didn't know there was a material science course when I was an 18-year-old. But once I got to university, it was a great bunch of people. It was a small department at Sussex, and they're really engaging lectures and topics to do research on. So I joined the material science team, did my final year project in the department, and took lectures from both engineering and from chemistry to get a material science degree. After Sussex, I continued what would have been my final year project on the Morse alloys and started work at Cambridge doing research there. Then I joined ICI as a research scientist and joined the science group, which I'll talk a little bit more about in a minute. I had a secondment to ICI Explosives in Canada. Again, I'll talk a bit more about that in my talk. And then I came back to the UK and I was continued research in ICI, what was ICI CMP Group, Chemicals and Polymers. In 1996, I completed a commercial assessment and I became a technical sales manager working for ICI Catalco at Billingham. And I stayed with that catalyst business until 2006. During that period, it was bought by Johnson Matthey. So I left as a Johnson Matthey employee in 2006. I'm not going to go into detail. I'll just talk a bit more about the end about what I did next. But basically, I set myself up as a consultant to do business development work, but actually ended up being very involved in STEM education and training, which had been long been an interest of mine. I will talk about that as a little bit more at the end of the talk, after I've talked about some of the materials projects. So I'm back to some of those pictures in a minute. So is everything showing well and you can hear me clearly?
Yep, that's fine.
Brilliant. I'd like to be speaking to the ether. So here we go. Back in 1982, the New Scientist had a picture on its cover, metallic glasses, attractive new magnets. That was the year that I was finishing my first degree and starting my final year research project. It was very exciting. What were these? Normally, most people I think on the call will know that metals normally form crystals and are crystalline materials. So what are metallic glasses? These are alloys that if you cool them very quickly before they can crystallize, you freeze in the structure of the melt. So it's an amorphous, non-crystalline structure. And why might that be interesting? We'll come on to. But I actually made these materials myself in the lab. So you basically take the alloy and you induction heat it in a quartz tube with a small hole in the bottom, a nozzle. And once it melts, it flows down through the nozzle, lands on a very fast spinning copper disc, which obviously withdraws heat quickly away from the thin ribbon of metallic glass, and there are no crystals in there. It's a random structure of atoms. Obviously, you can't do that with pure metals. It has to be an alloy, and it's the typical alloys we work with were iron, nickel, cobalt with a small amount of a metalloid, which is, boron, silicon, and phosphorus. And that's what it looked like. It's a picture not from my lab, that was from a lab in America, from the New Scientist magazine. But that's actually what it looked like when I was spinning the metallic glass across the lab. Quite exciting. And I didn't make metallic glasses quite this volume or thickness as part of my research project, but it was interesting. So there's the time temperature transformation diagram. If you look at the dotted line curve A, and note the quality of this diagram. In those days, everything was hand drawn. So that's a diagram, a TTT diagram that I hand drew. So taking the following curve A, start with the melting point, and as time goes on, you're cooling it down past the peak crystallization point, which is Tn, so you're avoiding crystallization. Go through Tg, which is glass transition, which effectively freezes in the structure, and down to room temperature. Of course, you can actually form crystals if you reheat it. And curve C shows how you would form crystals. You would have to heat it up through to a temperature Tx, and Tx is the crystallization temperature, depending on how quickly you heat it and other factors such as the composition, and you can actually create crystals by reheating it. So that's a little bit of background. Why would we do this? Well, the reason we were interested in these materials, and there was a hint, was on the cover of the New Scientist magazine, is these alloys in the amorphous phase have high magnetic susceptibility, low coercivity, and high electrical resistance. And why are those properties interesting? This means that when these materials are used for a transformer, the eddy currents are much lower, which means there's less losses from eddy currents. When you have a transformer, you subject it to an alternating magnetic fields, and currents are induced. If you can prevent those currents, then it doesn't heat up as much, you don't have as many losses. So it was identified that these could be useful for transformer magnetic cores, and also another potential application was for theft control passive tasks. When you take your item of clothing out of a shop and the tag hasn't been removed, the alarm goes off. That sort of application. So sorry about the blank screen. There's a picture of these nice metallic glasses. Mine didn't always look as beautiful as that. The studies I did were kinetic studies, so looking to see how stable these materials are, what happens when you crystallize them. So the typical, it's quite academic studies. I'd be looking to model of the crystallization, the nucleation, and the growth, but doing experimental methods, using experimental techniques to look at how the crystallization progressed, resistivity changes, using differential scanning calorimetry was a really good technique to observe the crystallization. And there's, again, hand-drawn micrographs. This is a cross-section of the very thin tapes or ribbons that we formed. And you can see a difference between the bottom surface of the ribbon is the bottom side of the cross-section. And you can see how the surface that was in contact with the quenching wheel forms more nucleation sites and more crystallization took place. So that's just a quick whistle-stop tour for the sort of work that I did in my academic research. So basically working on the same sort of materials for around 4 years. How it was different when I joined industry. So how did I join industry? These are some pictures of the Cambridge department where I did my work on research on amorphous metals. That's in Pembroke Street, the bottom one. Behind those windows was the lab where I was doing the metallic glass spinning. The big tower is the former Materials and Metallurgy department at Cambridge. They have now moved to the new museum site, but that picture was taken quite recently. It's occupied by somebody else now. So that building on the top right is where I did the microscopy work. And there's a picture of the college that I attended, Corpus Christi College. The reason I put that in there, it's quite interesting because prior to the year I started, no women were allowed in college. To study at the college. So I was one of 4 postgraduates, with the first women to study at the college after, I think, about the calculated, but a number of centuries, shall we say. So in final year of my studies, I spotted ICI was running an industrial orientation course. And I thought, well, I'm really interested in getting a job in industry. So I went along, and that's me. Of course, you don't recognize me at all. A long time ago. And I was very privileged to be offered a job in the New Science Group, which had a base at Wilton near Redcar, but also a base at Runcorn Heath in Cheshire, which I joined the department and the New Science Group department, which did research on behalf of all the businesses in ICI. The building to the top right is the research labs, and the bottom left hand corner is the commercial building. And out of view is the industry, the chemical plants at Roxavish and Casterkelner that made many inorganic chemicals and continue to do so, but under the name of INEOS rather than ICI. So in the 1980s, ICI was known as a blue chip company, very famous. Everybody in the UK pretty much probably had heard of it. And we had a very charismatic leader, John Harvey Jones. I think a lot of people may remember him. We had high profile materials. ICI polyurethane was used for skis, shoes, and lots of other things. The polyurethane that is made on those plants is still used for the similar applications. It's owned now by Huntsman. Sorry, somebody's trying to ring me. I should just switch that off. ICI polyester was also used in Olympic tracksuits. And sorry, my slides. The ICI Perspex, you can see it, international squash event, ICI Perspex, all over that. And ICI even sponsored a Formula One racing car. So it was quite a company to be joining in the 1980s. And lots of interesting materials to work on, including some of the following ones. Not just metallic alloys, but ceramic springs. I didn't work on this, but it was invented by Derek Birchall. Heterogeneous catalysts made at Clitheroe, dyes made at various sites in Blakely, Grangemouth, and so on. We owned a lime quarry. ICI owned a lime quarry, and I'll talk a bit more about that in a minute. Oops, wrong way. Plastics. The Alfa Romeo car pictured here at an Alfa Romeo event at Raby Castle last year actually has panels made from ICI Modar, which is a glass fiber composite with acrylic resin, apparently, and it was used in the SZ and the RZ models. The selling point was its high impact, and it didn't rust, which is a great benefit for cars in the 1980s that had a tendency to do that more than nowadays. Also fertilizers. Solid fertilizers contain the nutrients needed for plant growth, such as nitrogen, phosphorus, sulfur, and potassium. And that comes in different forms, so there's some material science involved. Many of you based on TSAB will know about the tower. See what was the old ICI towers as you go over the A19 flyover, the Prillin towers, where they have a melt of a fertilizer at the top and they spray that, and by the time it gets to the bottom, you've got little granules or little prills of fertilizer. But fertilizer is also made by granulation methods and so on. So some interesting materials problems there. I didn't have a map from the 1980s of where all the ICI sites were. This happened to be on Facebook the other day for 1955, so I picked this one. But the main sites hadn't changed that much in the 1980s. So sites all over the country, and ICI New Science Group, where I joined, did work for many of them. I've just put the list up together now, and then these are the ones I'm going to talk about in a little bit more detail. So I joined ICI New Science Group and worked in Process Technology Group for Professor Roger Davey. He became a professor at UMIST after after leaving ICI, and he specialised in industrial crystallisation. So any industrial crystallisation issue throughout the ICI family would quite often end up on our desks, our team's desks. We looked at both inorganic and organic compounds. As I mentioned before, Blakely in Manchester, Grangemouth had fine chemical problems, fine chemical manufacturing, and at Runcorn we had lots of inorganic chemicals, which were crystalline materials, and even at Wilton there were crystalline materials such as terephthalic acid, and I'll come on to that. So what we were doing is we were helping optimize the industrial crystallization, the big crystallizers, and also looking at modification of crystal growth, and I'll come on to that a little bit more at the moment, preventing crystal growth or changing the shape of crystals, that sort of thing. I also talk a little bit about propellants for airbag inflation, that's car airbags, which I worked in Montreal. Some more inorganic chemicals at Runcorn, some work on limestone and lime products, which was based in Buxton, alumina fibre, Saffel alumina fibre, which was manufactured and still is at Widnes, and some work I did with colleagues at purification catalysts and absorbents, which are made at Clitheroe, it's based in Billingham, and some organic metallic catalysts. So that's the list of things I'm going to whiz through now. Starting with industrial crystallization. So this is the work I did when I joined a new science group, worked there for about 3 years. And what we did was a combination of computer modeling and experimental studies. So we were looking at the structure of crystals and how organic chemicals interact with the surfaces of those crystals. So we did computer modeling. It wasn't as sophisticated as it is now, but we did have a very big computer that allowed us to model the organic molecules and the crystal structures and look to see what the matches were between the crystals of particular shapes and the surface of the crystals. So we were looking for potential relationships which would allow the molecules to block growth on particular crystal faces, which would either stop growth completely or change the shape of the crystals, because certain crystal faces would be selectively blocked from growing. So some real applications of that were barium sulfate, spelt the old way, scale prevention. And you've got oil fields when the seawater mixes with fresher water from the oil well, you exceed the solubility limit for barium sulfate, so you get a precipitate forming in the pipes, and obviously that's not a good thing because the pipes will get blocked and the flow rates will decrease. So our team did work on diphosphonates, which did a combination of experimental work and also some modelling, which showed that the phosphonates sat on the crystal face where a sulfate ion would have been able to sit, but blocked other sulfate ions from adding onto the crystal and growing. So that work, I think, was published eventually in Nature. And if anybody wants a reference, I can dig that out. Another area where we were allowed to publish was some work we did on terephthalic acid. Terephthalic acid is a component of polyester, and it was made at Wilton. I think the last plant that was taken down a few years ago was T8, and so was T7. And basically, under certain process conditions, metastable crystals were formed with different shapes and structures, and this had different physical behaviours, might affect processes such as filtering and drying. So we did some investigations, quite academic investigations into the different crystals, looking at the different crystals and whether they were stable or metastable, and understanding the phase transitions. So yeah, there's quite a lot of variety. We generally worked on crystallization of organic chemicals, and both organic and inorganic chemicals, as I said before. So that included salt. I mean, there are different crystal forms of salt required for different applications. for different rates of dissolution and so on. And at Fine Chemicals Organisation at Blakely and Grangemouth, we did some work on the dry dye crystals, which are obviously very different from salt in terms of molecular structure. The other bit of work, oops, sorry, did I hear? Okay. We did some work with ICI Pharmaceuticals, which is now AstraZeneca, mainly done by my colleague, and looked at how you could use crystallization to separate optical isomers. Some of you will know that some chemicals have chiral, and you can form two different types of isomers, and in they have different interactions with the body, so they have different pharmacological activities. And obviously, if you've got a drug, you want a particular one that's going to be the most active and do the right thing in the body. So crystallization is one method of getting the right optical isomer. Even although I started off as a sort of metallurgy, material scientist, a physical chemist, we even did some work in genetic engineering. We sponsored a project at UMIST, it's now University of Manchester, an industrial PhD to look at ice nucleation. It's known that Arctic and Antarctic fishes have antifreeze molecules in their bodies which inhibit ice crystals forming, and also some plants and some have managed to survive in quite icy conditions by having the surface of the leaves has lots of little crystals rather than big crystals that will pierce through their cells and break up the cells. So we did some, we sponsored some work which looked at expressing proteins or polypeptides from a bacteria to promote ice nucleation. Right, so as mentioned that I was seconded to Canada. For those of you who can remember back to the 1980s, no cars had airbags like they do now. I've probably got half a dozen in my car, but no airbags. We just kind of, not that many years before that, seatbelts had been made compulsory. But there was a bit of resistance to wearing them, maybe particularly in the US. So the project I was working on was one of the responses to the fact that people wouldn't wear their seatbelts. The alternatives considered were automatic seatbelts, where you sit in the car and the seatbelt automatically comes and fastens you in, and airbags is another option. So the driver was from insurance companies, actually, because obviously they were having to pay out a lot of money when people were injured, but then this was followed by legislation for safety reasons. So the initial developments were for luxury cars. Lincoln Continental and Rolls-Royce are two of the cars mentioned. And how did ICI get involved in this? Well, ICI had a joint venture with a car component supplier to supply the chemicals for the airbag. So the chemical is a propellant. ICI Explosives, or CIL in Canadian Industries Limited in Boulogne, Montreal manufacturing. So ICI's involvement was to make the gas-generating compound, which was sodium azide. Sodium azide reacts on the application of heat to form a lot of nitrogen gas and sodium. So we had other components, obviously, in the mixture. This was a powder which we mixed with other chemicals, and the other chemicals had various effects, but one important thing was to react with the sodium to form an inactive, you don't want molten sodium or sodium oxide, which is alkaline. So you had to choose other compounds to go in and make that, neutralize that metal. The other thing we had to do when we formed the pellet, apart from having all the right materials properties, we had to make sure that it burned at the right rate, which meant we actually had a cylinder with a pattern of holes running through it. ICI had a lot of experience in manufacturing explosives for the construction industry, and also the detonators that set the explosives off, where it has in common. sorry, and also a similar sort of principle to solid fuel for rockets. Back in the UK, I moved to ICICMP Limited and ran the research group, one of the research groups in the acid and salts business. My team worked on improving the processes. The plants were very old and they needed quite a lot of TLC, and they were commodity chemicals. So we were looking to get added value by, you know, changing the product form in a way that we could get more money than just the base price for the pure chemical. So some of you, again, another trip down memory lane. In the 80s, laundry tended to be just washed in powder. You go and buy your packet of powder, throw it in the washing machine, and that was your choice. But now, obviously, we have a whole range of choices. We have liquids, gels, we have tablets, we have little gel in plastic. But this time, the choices, the major detergent manufacturers got in touch with ICI and asked us to provide a stable dispersion of sodium perborate. Sodium perborate was one of the many chemicals that ICI supplied to the detergent industry. It acts as a bleach when sodium perborate hits hot water. Hydrogen peroxide is produced, which forms a bleach, acts as a bleach. Our challenge was to manufacture a stable dispersion of the product that would then remain stable when it was mixed with all the other products that go into a laundry liquid. These include bulking agents, optical brighteners, fragrance emulsifiers. So it was quite a challenge. We managed to make a nice stable dispersion. Then we had some challenges as we then mixed it with some of the other chemicals and components of the mixture. Anyway, that business actually closed down, but obviously there has been success in developing laundry liquids. The lime quarry that I mentioned earlier was another part of the portfolio. ICI operated a quarry near Buxton, and the quarry is still there, now operated by Tarmac. And what we were looking at is trying to add value to commodity products from limestone. That's the picture of the quarry, courtesy of the Steam magazine. That was the educational magazine that was circulated around in the 1980s. We had kilns which produced the quicklime, basically heat the limestone to 1200 degrees and K, and you form calcium oxide, and carbon dioxide is given off. And then if you add water to that, you can form hydrated lime, or sometimes it's called slaking. And some people might remember some of these terms. If you add water to it, you can form milk of lime. And who can remember milk of lime from chemistry lessons, testing for carbon dioxide? So what we were doing is trying to add value to these pretty much commodity products. So we were looking at different product forms for different applications to meet different specs of customers. Pretty much the biggest use of lime products is in water treatment and construction. There's some pictures of limestone being sprayed on a Scandinavian lake to neutralize the water which has been affected by acid rain. Not so much of a problem now, but it was a big issue in those days. And also, if in construction, if you have a clay soil, it can be stabilized by addition of lime. Also another big application of lime is in when you burn coal, it contains acid gases, HCl, mainly sulfur dioxide, those sorts of SOx, NOx. So basically you can spray lime or components of lime as the gases, the combustion gases are formed, to remove those acid gases. And quite often you would form something like calcium sulfate, which is gypsum, which can also be used in construction. So we were looking at coating the product, granulating it, producing slurries, controlling particle size distribution to get the reactivity and the effects that the customer required. Right. The last main technical project that I worked on, I was technical manager at Safil, which is an alumina fiber. Safil still exists. It was bought by a number of different companies after ICI sold it. So it's an alumina fiber. It's very pure because it's made by a chemical route, a salt gel route. So mix the chemicals together and then fire it in a furnace, and you spin it, you fire it in a furnace, and you get a very high purity alumina fiber, which means it has high temperature resistance. It is a highly resilient fiber. Low shot, that means there aren't many particles. It's almost all fiber. There's lots of benefits to that. It was developed to be a safe fiber. That's where the name comes from, Safil, safe filament. The fiber diameter is more than 3 microns, unlike some other fibrous inorganic materials we know which aren't so healthy for our lungs. What our team did was develop product forms which were easier to handle. It's used in insulation, and as it's spun, it forms a thick blanket, and what we wanted was something that was a bit more compressed, that could be easily processed when people were using it in high temperature furnace insulation. Other fibers, you can actually just press needles through, and the fibers are drawn through the fabric and through the blanket and compress it to low thickness. That doesn't work with Safil. What we had to do is to put an organic layer, a polymer layer on the top, and do stitching through, and the polymer fibers formed allowed the product to be compressed, and then when it's used in the furnace, the polymer burns off. So that was a very successful, and then looking on the website, they're still using that method today. And one of my exciting visits when I worked for Safil was to crawl around the ethylene furnace at Wilton when they were relining it with Safil fibre. Not for the claustrophobic. Safil has also been used by NASA and other highly specialised applications. That wouldn't pay for all our bread and butter, but it is quite prestigious, has some very interesting applications. We had a sister product called Safi Max, which received some European funding. Before I go on to that, I just want to talk about some automotive applications. Using the properties which are also useful for insulation, high temperature resistance, resilience, and high purity of the fibre, forming it into a mat, similar, encapsulate it in a polymer sheet. It was used in a catalytic supporting a catalytic converter in some cars, and I believe it still is today. Basically, the monolith which supports the catalyst is made from a ceramic and quite brittle, so there's degradation in the car, which obviously has vibrations. So the Safil blanket was wrapped around the monolith to cushion it at high temperature from the vibration, and that was used by some well-known motor manufacturers in Europe. The other product I wanted to mention was Safi Max. So we had a pilot rig at Widnes to make a continuous fibre by the same method, and this was used in a European project and demonstrated that aluminium engine blocks could be reinforced with that Safil fibre. I don't believe that went any further. I haven't managed to find any references to that, but not all our projects went to commercialisation. So when I was working on Safil, I enjoyed working with customers. We did lots of customer service work, and I applied to become part of the commercial team, and I was successful. And I was recruited by ICI Catalco to work on to be a technical sales manager, and that was in 1996. So the project I was given was to look for new applications of a group of products called PuraSpec. Catalysts, ICI catalysts, and all catalysts are easily poisoned by impurities. So ICI had a range of catalysts and absorbents that absorbed the impurities in gases and so on, reactants, before they reached the catalyst. And my role was to look for some new applications for these. So hydrocarbon olefin purification was one, removal of sulfur compounds and trace metals, which were in the feedstock because of its origin, you know, from oil and gas fields. And depending where the source of the feedstock was, different set of impurities. Another application was to look at purification of carbon dioxide. From not the carbon dioxide that's made, say, from the ammonia process, but the carbon dioxide that naturally occurs from various volcanic sources. Carbon dioxide from those sources is often added to water and other beverages to make them sparkling. But sometimes as anyone who's been to a volcanic spring, it's quite often you smell sulfur and other compounds which would taint the drinks. So my role was to go and visit throughout Central Europe to sell carbon dioxide purification products. Of course, I also visited petrochemical sites in places like Holland, Spain and Germany to sell the same catalysts for purification of olefin feedstocks and so on. So my final role in my final business that I worked for in Johnson Matthey was organometallic catalysts. So that's homogeneous catalysts. The previous products, the pure spec products, were solid heterogeneous compounds. So worked for the Vertec business, and I found out recently that Vertec stood for versatile technology, and organometallic titanium and zirconium products were made at Haverton Hill. And there's a picture of part of the Haverton Hill plant, and it's black and white, but that was 2005 when an investment was announced. The plant, I understand, doesn't run anymore. The business was bought by a overseas company, but at that time, the products made there were used as additives for inks and coatings. If you, for example, on a crisp packet, on a crisp packet, it's many layers, and you want to get the inks and the layers sticking together and the inks sticking to the layers. So the titanium organometallics and zirconium organometallics are promoters for adhesion. They're also used in homogeneous catalysts as homogeneous catalysts for specialty and fine chemical production, such as additives for polymers, plasticizers, and so on, in both the pharmaceutical and fine chemical industry. We developed some new products, including a titanium-based replacement for the established antimony catalyst for polyester. Antimony is a catalyst that's used to make PET. Not want to alarm anybody, it's not very toxic in the level that it's in plastic bottles, but in the handling in the plant, you know, there's potential exposure of workers, and also you have to lose quite high levels as a catalyst. I'm looking at a plastic bottle here, you have quite high levels of catalyst to get activity, whereas much lower levels of our organometallic titanium catalyst could be used. So that business was then developed and run by a company in Stockton-on-Tees called Catalytic Technologies. Lots of resistance though when you're introducing a new product. It will mean a big change to lots of processing plants that take the preforms and make them into the actual bottles. There's lots of plants that use the antimony catalyst, which the behavior is well known. When you use the catalyst based on titanium, it changes the way the polymers behave and process. So there's quite a lot of resistance to change. But there was interest back in the early 2000s, and we were quite positive about it at the time. The last business I worked for not the last one, but one of the last businesses I worked for in 2002 was working for the Cairo Catalyst team. They had a team at Teesside and they wanted to relocate to Cambridge, where there's more pharmaceutical companies were located at the time. So this is a picture of the building that I actually took last year when I went past. Still there, still hosts as a research group for Johnson Matthey now. And they were looking at Cairo catalysis for the manufacture of pharmaceuticals, set up a new lab, and not only that lab, they've got a nice shiny bigger lab around the corner. The picture at the bottom left with the black and white picture is adjacent to my old office on Haverton Hill Road. You can't see very clearly probably, but some people will have noticed as you've gone past now, that's become a self-storage place. Behind it, you can still see some of the chemical industry of lucite that still exists in the location. Right, that's end of me talking about material science. What did I do next? A little bit of my career. I left Johnson Matthey intending to set up as a business consultant, but very quickly got into something that's very dear to my heart, is education work. So I worked with an EPIC education group, and EPIC is the North East Process Industry Cluster. At that time, they had an education group, went into schools, promoting industry, science, chemistry to young people. I joined the Chemical Industry Education Centre, which was sponsored by industry and the CIA at the time, to take science and industry into primary schools. So on the left-hand side, although it's not a very big picture, you can see me with a little girl showing her how to make a heat exchanger out of a 2-litre drinks bottle and some plastic tubing. And then, so we did it in the classroom. We did experiments in the classroom, and then we took the children in the industry to see the full-size real industrial equipment. And below is a picture of some young people at, I believe, Lucite from a local primary school. So that actually, the benefit of that was to encourage children to think about careers in industry, to encourage a love of science through doing practical work, to build confidence in the teachers so that they weren't nervous about doing experiments, because quite often primary school teachers aren't scientists. Okay, so the next job I did after that was I was asked by NEPICS to help with their apprenticeship program, and following that I became a project manager of some business support programs where we were helping small companies in the Tees Valley and throughout the Northeast engage with the larger chemical industry, helping them show their, develop markets for their products for the chemical industry using my industry knowledge. I left NEPIC, I became membership director at NEPIC, and then I left 2 years ago to join Industrial Technology Systems, and I have responsibility for the sales to the process industries. Many of my customers are in the area. What we do at ITS is just summarised here. I use my knowledge of the industry to help customers choose the right process control systems, ensure they've got the right regulatory compliance in place, supply project management or engineering if they're required, which is, when there's a shortage of engineers or specialist engineers, non-core engineering, we can deliver, and also extends to management information system and vision systems. The founder of the company started at ICI and did industrial automation at ICI, and then set up his own company 30 years ago. One of the things that I like about working for ITS is that quite a lot of the members of the team are involved, like I am, in STEM ambassador programs and children challenging industry, and we have a number of apprenticeships. So we're looking to inspire the next generation for careers in industry, for careers in engineering or science, and offering opportunities for people to come and work with us. The company also does quite a lot of work in the local area in terms of supporting hospices and local sports teams. So I'm at the end of my talk now. Whistle Stop Tour, hopefully people have found it interesting. I'd like to thank ITS, my company, for sponsoring, and the colleagues throughout my 35 years in industry for all their support. I'd also like to thank you for listening, and my colleague Carol, who helped put the slides together for me last week. Those are my contact details if anybody wants to get in touch. We're always happy for a chat, and about old times or about the future. And obviously I'm looking forward to being president of the CIE this year. Thank you very much.
Thank you very much, Joanne. That was very interesting. I don't know whether anybody apart from Mark has managed to discover the chat button at the bottom right hand corner. But if you want to type some questions in there, then that would be most welcome.
Thanks for the applause, Colin.
Yes. I'm just trying to unmute everybody's microphones, but for some strange reason, the unmute all button doesn't seem to be working. So I'll maybe have to do you all one at a time. While I will abuse my position and ask. Obviously, the chemical industry has changed quite a lot during the recent years, as has the steel industry. I mean, when we first moved up to Teesside, British Steel and ICI were the two major employers in the area. Unfortunately, the steel industry has gone into a fairly sharp demise. I know that the chemical industry is much fragmented, but is that also in demise, or is it rising, or is it more or less the same?
Oh, am I the right person to give an overview of that? I'm not sure, but there's a number of different elements here. So there was a big challenge from the Far East and China in that their labour rates are much lower. They can build bigger, they're building newer, bigger, more economic plants. So that's a challenge. A lot of the UK chemical assets are quite aging. So they're not maybe as efficient as some of the ones in the Far East. However, we've got, a really good background. We've done the investments. We've got great people, lots of knowledge, a really good engineering ecosystem. So there's a number of companies that I work with on Teesside who are very successful and they've got a good future. It's just different, but obviously the chemical industry isn't as big as it was in the UK as it was many years ago, and it doesn't employ as many people. Some of the factors is a lot more automation than there used to be.
Right. People should be able to unmute themselves now. There should be a button at the bottom of your screen that should say unmute, and if you click on that, you should be able to make yourselves heard. Are there any further questions?
Yes, I'd like to ask a question.
Go ahead, Don.
Can you hear me?
Yes,
Don.
we can.
Yeah.
Hi, Don. Nice to see you.
Yeah, Joanne, I thought your talk was very interesting. Well done,
Thank you.
and illustrates a very varied career. I can only wish that when you left ICI, or when ICI was disbanded, that you didn't come for a job at British Steel. But you can still start on Monday if you wish.
Thank you, Don. I think the big difference I felt like from academia was that we worked on the same product for many years. Whereas in ICI, it was all about moving. Oh, this is the next problem. This is the next problem. So I had to come up to speed very quickly, identify who the experts were, and tap into their brains. And I mean, I presented work today that I couldn't have done by myself. It was all about teamwork and assembling the right teams of people, the experimentalists, tapping into the molecular modelers and the computational people, and bringing them all together to form the right team to solve the problems. And that's what I really have enjoyed and continue to enjoy in my career, getting the right team of people to work on the, solving the problems and advancing the technology.
Well, I would agree with you that teamwork is very important, certainly to British Steel as well. I was interested by your reference to heterogeneous catalysts.
Oh yeah.
Later on in your lecture, you changed to homogeneous catalysts.
Yes.
So you'll be interested to know that people like myself are working. Well, I'm working on heterogeneous materials in the steel industry, and indeed the steel industry on Teesside in the 1800s, 1700s, 1800s was built on them selling an heterogeneous material, in that the iron, the steel which they made, well, they didn't make steel, they made a kind of low carbon iron, and that comprised of Fe and slag. And, you know, some of these materials are worth readdressing to see what properties they can bring to, you know, using the technologies that we have now. So well done on your lecture. I really enjoyed it.
Thank you. And, you know, if anybody wants, I probably haven't got time tonight, but if anybody ever wants to come and have a chat and we can explore in a bit more detail. I mean, it's taken quite a lot of time, but I've really enjoyed going back through my old archives and reminding myself of the different things I've worked on. I noticed that somebody put a question about publication, and that was something that was a real challenge to us. I can't see the actual, I think you sort of floated up on the screen, has disappeared again. But
Right. So,
what was
well, it was a question from Stuart Millman, and I'm aware Graham Hillier's got his hand up as well. What
yes,
Stuart said was, Joanne, a very wide range of activities in your remarkable career. You were largely involved in highly commercial projects.
yeah.
Overall, were you allowed to publish results at e.g. ICI Johnson Matthey, or were you restricted, as British Steel, up until the mid-1990s?
Yeah, it was a real frustration that we discovered some quite interesting science, but for commercial reasons, ICI didn't want us to share it. In fact, they weren't even really keen on patenting it. They wanted to keep it quiet. But we did, as I worked with Professor Roger Davey, and we did get some publications out of some work, but we did a lot of stuff I can't even talk about now, because I'm not sure on the commercial sensitivities. I've talked about, you know, processes that I know it's in the open domain, but yeah, it was a frustration because we were working quite a lot, collaborating a lot with universities and colleges, and it was frustrating for the academics that collaborated with us as well. We did get a few papers out.
Graham, you had a question. Glad you've sorted out your computer.
Yes, so am I.
Hello, Graham.
Hi, Joanne. That was really great. I mean, you worked on loads of new products that just about got to market before the company you worked for gave up on them. And there are other companies making a lot of money out of them now. Do you have a view about what the UK could do better to stop itself inventing everything but not making any money and losing it to somebody else? I haven't got one either, but by the way, it's quite a difficult question.
It is a difficult question. Obviously, government's invested in, some catapults and CPI and companies like that because they recognise there's an issue, but there is a problem, isn't there? That you need to get funding and somebody carrying you through that period where you haven't quite got the revenue in from the customer, but you're almost there.
Yeah.
But I was very lucky, for example, at Safil, that the company had actually paid. There were years and years of research and loads of stuff I could draw on that must have cost millions. And the company now is, the company who owns it now is reaping the benefits of that. But I don't think ICI would probably ever recouped its money and its investment in that product.
Yeah, I think, I don't know. I think we have to start being a bit more serious about running businesses rather than inventing things. We love doing research in the UK, but we seem to have forgotten that spending loads of money on research and just giving it all away isn't a particularly good way to make money.
Yeah,
and even CPI struggles to get stuff in the UK.
And of course, we don't encourage it with academia because it's
no, we don't.
Because it's all about number of new papers and so on, and people have got to always be finding something new, whereas perseverance on some of the stuff that might bring more commercial dividends. I don't have any answers, but so yeah, Seen quite a lot in my career.
Yeah, takes a long time. I mean,
It does.
I did single crystal turbine blades in 1984, and it was only 3 years ago that Rolls-Royce built its first single crystal turbine blade factory. So that's 40 something years.
Well, indeed, and you know, it's good to see that Sapphire's still
Cheers.
being sold, and some of the other products I worked on, you know, they're still, you know, some of the chiral separations and so on. That's still a big thing.
Yep, the polyester catalyst thing's beginning to get adopted as well.
Right. Well, that's where I did kind of left people hanging a bit because I hadn't always been able to find out, well, where is it now? You know, I left it, you know, 10, 15, 20 years ago. What's happened in the meantime? So yeah, that's why I'm interested if anybody's got any information to have a chat about it.
Does
I'll
anybody
find out if I can tell you what I know.
does anybody else have any questions? Keith, yes.
Yeah, it was a great story, a great career, and I was very interested because it started with material science. I also started in materials, but actually metallurgy, and I was always considered a failed physicist because I went into material science. Now you're talking to young people, do you still advocate material science as a good career starting path? I mean, for me, I think it's a great career starting path, but what's the view on material science and the future careers opportunities for young people?
I'm not that specific really, probably, when I talk to young people. So I'm talking to them at quite a young age, and all they really know is either science at primary school, or if they're at school, they know chemistry, maths, physics, biology. They don't really know about engineering. They don't know about material science, the same as me when I was their age. So I think most people can, if they get into university studying the science, then they can find their route, you know, things they're interested in. My daughter, for example, you know, went to university to study physics, and she's ended up doing something a little bit different, but still science. So that's the wonderful thing about the right university course. You can actually, you know, find what interests you once you get there. I think, you know, we are making roads into getting more students going back to studying science. I mean, I was very sad because the material science department that I was studying at was closed the year after I finished, and quite a lot of the material science departments went the same way back then. Even chemistry departments were closing, but hopefully that's been reversed with the increase in numbers going to university. I'm not sure if I really answered your question.
I think it's good. I just, you know, I went from material science, metallurgy into engineering. You went down a different route, but it always seemed to be, I got interested at Nuffield physics at A level, was where I got the spark. And
Yes.
It was, I think, a great choice. And I just wondered how well are we talking about these opportunities and showing careers like yours to young people that it can start from anywhere.
Yes, I think that's it helps if you're doing science or engineering, but yes, it doesn't matter. I mean, as I say, I did biology, I did physics, chemistry, engineering, all sorts of disciplines during my career I needed to draw on, and being a material scientist was quite helpful because I had that multidisciplinary background. Not biology, but I picked that up.
I've got a few comments in the chat box here. Dave Martin says, on the subject of long-term commercialisation, it's interesting to note that amorphous core power transformers are gradually making an appearance on the electricity distribution network, albeit on a trial basis.
Well, that's really excellent news, Dave, because I hadn't been able to pick up. I mean, if I rang my former colleagues at Cambridge, they probably would have kept me up to date. I just didn't have enough time. But yeah, it's really great to hear that they're gradually being introduced.
And Graham Hillier adds that his son is doing materials science at uni. It's still a really important subject for those that find it. Yeah, and I must admit, I had no idea that metallurgy existed when I went to university. I started with a general science degree. Marcus Hamler spot on, I think. I'm a failed physicist. Kids just need to stick with STEM and find their own paths. Back to Graham Hillier again. The Millman Scholarship at MPI are important here. Well done to Stuart. Anybody else? Any further comments or questions? Oh, hang on. Another comment from Stuart here. It may be too late for young people to make decisions on materials science, metallurgy, engineering once they reach university. It's surely at school that STEM options should be taken up. Yeah, but I mean, you couldn't do engineering at school, certainly not when I was at school. So I don't know how.
Yeah, it's a very special school that can share all that has the expertise to talk about the different options, and that's why it's important for people like us from industry to go in and talk to the children and about different options.
Yeah,
and
I
where
mean,
it can lead. Yeah.
I think kids who get good science teachers are very lucky, because obviously there are a lot of other things that people with a science degree can do, but less so history or English literature or things like that. So there's always a shortage of good science teachers. And I suppose there's nothing worse than being taught science by somebody who's not very good. That's really going to put you off, isn't it? Further comment from Graham. Perhaps the school stuff is a thing for CIE. Now we have Joanne at the helm. Well, there you are. There's a challenge for you to pick up, Joanne.
Right. Well, I still do the school stuff. I'm on the advisory committee for the Children Challenge and Industry program on Teesside, and I do mentoring with young people, STEM, people who are interested in STEM careers. There's lots of, as a STEM ambassador, there's lots of opportunities, and if anybody wants any ideas of things they can do to make a difference, always happy to share.
Colin Woodward now says, I have links with Durham University. Students can change course after, say, 1 year, and often do. Yeah, and I'm one of them. I went to Durham and I changed my course after the first year. So
yeah, I think the important thing is to get in doing a science or an engineering subject, and if you do well enough, usually in your first year exams, then usually there's options if you want to change. Okay.
Yep. Okay, well, I think that just about wraps it up. Marcus is sticking his thumb up.
Thank you, Marcus. I used to work with Marcus many years ago.
Oh, good.
There's a few people on here I used to work with.
Yes.
Mark Lewis, Graham. Well, Graham and I used to be on adjacent coffee tables at Cambridge. In that time.
That's a long time ago, isn't it, Joe?
Yeah, you had a beard then. And
Scary,
Colin and I
were
colleagues at ICI Catalco, and Amanda and I worked together on schools programs. So there's a lot of people here I know. So cool.
Right. Well, I think at that juncture we'll wrap it up, and I'll thank everybody for attending. If I can just share my screen a minute, I'll show you the poster. Yeah, that's. Oh yes. Can anybody see that?
Yes.
Right. So that's the prestigious lecture that we're having in November, on the 3rd of November, from Paul Butler, who's the CEO of the Northeast Automotive Alliance. And he'll be coming to talk to us next month. My screen's gone up totally doolally now, so I don't know what you're seeing.
I think people will have seen it in the newsletter. Yeah, thank you. Thanks to Paul, who was a colleague of Mark Lewis and myself at NEPIC, but went on to set up the Northeast Automotive Alliance, which has been very successful. And he's got lots of interesting things to tell us about the whole car electrification and program, which does have some impact on Teesside, because it's potential of the chemical industry makes materials for batteries here on Teesside, and there's potential for more.
Jolly good. A parting word from Amanda Elvenhill, who says Joanne is a great ambassador and role model for young people. So
thank you, Amanda.
Amanda. Anyway, at that point, I think we'll say cheerio and good night, everybody.
Thank you, Sue, for chairing.
Okay, thank you.